Hi there, folks. Welcome back to another calculus video. In this video, we're going to be talking about how to integrate the secant function. And this is something that doesn't really have an elementary antiderivative. We know that if it were something like sine or cosine, it would be pretty easy to solve, pretty easy to integrate. If we had something that we know integrates pretty well, if we had something maybe not secant, but what if we had secant squared? We know, of course, that would integrate very easily. But in this video, we're talking about how to integrate specifically secant to the first power. Now, we want to discuss possible methods we can use to do this, because there is an answer. I want to just kind of spoil that for you right now. The answer to this integral is the natural log of secant of x plus tangent of x. And it seems kind of a strange antiderivative, something that involves the sum of two trig functions in a natural log comes from something so simple like this. But I'll show you where this comes from. So like I said, we want to talk about possible ways to solve this. It isn't something you'll find on a typical integral table as far as the way you want to set this up. It doesn't really look like a substitution problem because we don't really have an inner function and an outer function situation, something that has something other than x as the inner function, and the derivative of that inner function somewhere present in the integral. We don't really have that. And it doesn't really look like an integration by parts problem either. I mean, if you want to give it a try, you're more than welcome, but this won't integrate very nicely if we use integration by parts. Another thing you might want to do right away is see if any of those trig identities would help us. See if there are any ways you could possibly write this in terms of other functions. For example, we know this is 1 over cosine. It's the reciprocal identity for the secant function that tells us this. And from there, you can try a few different identities you can find on the table. But I don't really feel like any of those are going to help much. So we've discussed all of those options. So it seems to me the only solution is to make this into some kind of a substitution problem. Write this in such a way that we can integrate it using u-substitution. That's just typically the way we do it. If we don't see something that integrates with our rules, typically all the rules that we've learned in this class, usually substitution is a pretty good way, but we have to rewrite it. We have to do some things. We have to manipulate this algebraically in a certain way before we can even begin to integrate it with substitution. So, and one thing would be really nice. It would be really nice if we could just maybe multiply it by something else. If this were perfectly legal in the laws of math, life would be pretty good, because then we have a u and we have a du, and we can integrate that very easily. But unfortunately, that is illegal. I've come to find out in the laws of math land, you can't really do that. You can't just arbitrarily multiply something by something else and keep the same value as you had before. So we're gonna do some kind of a modification of that. We're not gonna just multiply something by another function. We're gonna multiply this by a certain function, and we're also gonna divide it by a certain function. That way, we're still keeping the math laws happy. We're not going to get in trouble with the math gods for writing it in this way. This is just going to be 1. It doesn't matter what f of x is. We can write any definition we want. You pick any function for f of x. As long as you divide it by itself, that does not change the value of the integral. We still have the integral of secant of x dx. So the trick is to decide what function is going to help us. What function can we multiply secant of x by, so that we have something like this, so that we have a function on the bottom and then the derivative of the function on the top. Typically, things work out this way. Like I said before a few minutes ago, whenever you're faced with something like this and you know that there's a bit of u-substitution involved, there's automatically going to be a natural log involved when it becomes irrational. We know that we have something on top, we know we have something on the bottom, so that right there is just a dead giveaway. We're going to be dealing with some kind of a rational function, and that we're going to want to put it in such a form that we'll be able to integrate this using the logs, using natural logs or maybe other bases. But for now, I think it'll be just natural logs. So we want to figure out, what does f of x have to be so that we have a function on the bottom and the derivative of that function on top, so that we have something really nice like this that integrates perfectly. Well, let's talk about all of the derivatives that have secant, because we know the top of this is supposed to be du. It's supposed to be the derivative of our function u, yet to be determined. So let's see if we can think of any derivatives or any functions whose derivative has secant in it. Well, there's that example from earlier. This one has a secant in it. And then this one also has at least one multiple of the secant function in it as well. So ideally, we want the derivative of our function to be we want it to be one of these functions. We want to have this so that the derivative could either be this or that. We want du to either be secant of x times tangent of x, or perhaps maybe have the derivative be secant squared of x. But to me, it doesn't really seem like any of those are going to work, because if we were to pick tangent to be our u, this would be du, and we don't really have the tangent function anywhere in this integrand. So this one doesn't exactly work because we don't have tangents in the integrand, and then this one doesn't work because we don't have tangent in the derivative of the function. So we're going to have to make f of x into a multi-term expression. We're going to want to make it into secant of x plus tangent of x. And I'll show you why. So now that we have this definition of f of x, let's substitute that back into the integral. So it looks like we made it worse, but we've actually made things a lot better, and I'll show you why. So what I want to do is I want to distribute the secant of x to both of our terms in the numerator of our new fraction. We get the following. We get secant squared x plus secant of x tangent of x. And at this point, you might be seeing what I'm going on about. You might see what I'm up to and why I've rewritten this in the way that I did, why this is useful. So just a moment or so, I mentioned something about not having this derivative anywhere. And I also mentioned something about not having this derivative anywhere either, but now it looks like we have both of those. We were worried about setting this function to being du. That didn't work before, so we tried this one. We tried to say this could be du, and that one didn't work either, but now it turns out they both work. Turns out that all we had to do is multiply secant of x by some function, the same exact function on top and on the bottom, which is essentially just 1. We just multiplied our function by 1, essentially, and we've got it into the form that we do have the derivative on top and the function itself on the bottom. So we're going to combine these two functions. We're not going to have just a u and a du. We're going to have two u's. We're going to have u actually be not two u's. I might have misspoke there. We're not going to have two u's. We're going to have two terms in our u function. I'm not just going to set u equal to secant of x or tangent of x. I want u to be both of those added together. And the reason why this is working out so nicely is because we know that the derivative is already there. We don't even need to do anything else. We've already done all the heavy lifting. Secant of x gets us secant of x tangent of x, and then the derivative of tangent of x is secant squared. So what I want to do is I want to make this look more like what we have in our integral. So I think I want to write the secant squared x first. But I also want to multiply both sides by dx to put it into proper differential form. So we get du is secant squared of x plus secant of x times tangent of x dx. And beautiful. We have exactly what we're trying to find. We have exactly what we need. Going to clear away some of the stuff we don't need anymore. So let's rewrite the integral. Oops, erased the u. So we have a du on top, and we have u on the bottom. So of course this just integrates to the natural log of u. And it is an indefinite integral, so we want to make sure we include the constant. So now it's just a simple matter of putting u back in. So our solution is the following. Our solution is natural log of secant of x plus tangent of x plus c. That's it. That's our solution. Quick recap, we explored our options. We tried an initial substitution without modifying anything. We considered maybe integration by parts. We considered maybe doing some manipulation with trig identities, but none of those ended up working, and it turned out all we really needed to do is multiply the function by the same thing on top as we have on the bottom so that we could use u-substitution. So u-substitution, it seems really simple, but as you guys can see, there's a lot more than typically meets the eye with this method. It is much, much more powerful than the typical student realizes, but it requires a bit more understanding to understand how to utilize its full power and how to manipulate something so that you can use it. All right, well, I hope you enjoyed this. See you next time.